Hello. If you've ever used facial recognition to unlock your phone, then there's certainly some beautiful linear algebra at work. Today, we'll explore one of the more foundational methods, which is eigenfaces for facial recognition, which today is a little bit outdated and less powerful than convolutional neural networks, but is still a very interesting exploration. So the technique of eigenfaces uses eigenvectors and principal component analysis to turn faces into numbers and back, allowing the algorithm to recognize faces after being trained on a dataset. So let's start with how to represent a set of images as numerical data. So, for example, this may be a face, and it exists in a box of pixels, and I will draw 16 pixels. And so we could represent the RGB values of each pixel in a matrix, in this case a 4x4 matrix. And what we can do is we can project this matrix. So first of all, we're gonna write each um, each RGB value as a as an entry in a 4x4 matrix. So this is gonna be like a triplet, let's say, of integers, scale, or yeah, integers in this case. And then now that we have the matrix, what we want to do is we want to to project this matrix into a single row vector with 16 entries by combining each individual row. So all the way to C16. And so this is what we call our face vector. And this contains all the image data of a face in our data set. So now for normal resolution images, we will have much higher numbers of pixels in each face, and thus very large face vectors existing in very large vector spaces. So, for example, a 200 by 180 pixel image will become a 36,000 dimensional vector. But we want to find patterns in this massive space, and we simply don't have that much computational power. So how do we do this? So let's get into some principal component analysis, and start to solve this problem. So just so we know what we're getting into, when we want to represent any face with our facial recognition algorithm, we will represent the face vector face as the sum of a mean face uh, added to a linear combination of um, a very special set of vectors, which we'll get into what they are later. So that's how we're going to represent any face we're going to recognize. Um, so let's start with the mean face. So this is going to be taking all the images in our data set and say this one's black, this one's white, and this one's like alternate. This one's the identity matrix basically. So then the mean face might look like very gray here, and then slightly lighter in these regions. So the mean face is very easy to compute since we already have numerical representation of our image data. It's just the average of uh, the sum of all our uh, uh, face vectors, or even face matrices. It doesn't matter at this stage whether your data is in matrix or vector form. Um, so yeah, that's the mean face. And we also want to know how to get back to our training data faces from our mean face. So what we do for that is we um, compute difference faces for all of these face vectors. So the difference faces between the mean face for this, it would look like a lot of white. Yeah, pretty much a lot of lighter colors here, and then this would be just this matrix because it's completely blank, etc., etc. So that's the difference face. And again, computing the difference faces is extremely easy. We simply subtract the vectors um, from the mean face. And also notice that each difference face will vary slightly from each other, and they will vary in different directions. So from this, we can construct a high-dimensional cloud in which each face vector is represented by a point, and then they will vary more in certain directions, and we can call those like axes. Um, and so these are our informative directions, and we are going to want to find them. So we find the directions where faces vary the most using the covariance matrix. And the covariance between two variables is essentially defined as how the variables are related. That is, um, if say a positive change in x results in a strongly positive change in y, then we would have a very positive covariance. And the same goes for zero covariance or negative covariance. And in our case, we can construct the covariance matrix C, which equals our lists of difference vectors. Um, so this will be however many uh, faces we have, um, and however many pixels are in each difference vector, and multiplied. So this, we will do the transpose of this, and then multiplied by the the difference vectors themselves. And since the difference vectors, it has 36, each difference vector has 36,000 entries, and there are um, let's say we have a 76 element data set, so 76 there are 76 difference vectors in this list of difference vectors. This is a 76 by 3600 36,000 entry matrix, while this is a 36,000 by 76 matrix. So when we multiply them together, we get a 36,000 by 36,000 sized matrix. And this has billions of entries, which is too large for any or most programs to handle. So we have to simplify this a little bit in order to actually make use of this covariance matrix. But before we actually understand how to actually utilize the covariance matrix, let's discuss what we want from the covariance matrix. So essentially, we kind of want a basis for each axis of variance in each variable, and for that we will actually look to the eigenvectors of the matrix. And the reason we use eigenvectors is because they will diagonalize the covariance matrix, because C can be written as P dp negative inverse, where D is the eigenvalues of um, C, which correspond to the eigenvectors in P. And so that's how we use the eigenvectors to diagonalize the covariance matrix. And this allows us to create a one-to-one transformation from our original data set of all these faces to a simpler one, which is actually just whose basis is actually just the unit vectors of that um, of that high dimensional vector space. So this leads our data to be decorrelated, and that means that each axis has no covariance because each axis is simply perpendicular orthogonal to each other. So that's really good. We want that. Another thing is that eigenvalues actually determine the size of the eigenvalue actually determines how important that specific direction of variation is. So we can sort of sort which variations we will consider first, and that can save some computational space. And they also actually help minimize reconstruction error for any subspace dimension. Um, so yeah, so this is essentially the one of the methods of principal component analysis where you are trying to essentially break an object down into components which yield information about the whole, and linear algebra is very helpful in PCA. Uh, yes, so let's go back to our extremely large covariance matrix, which we want the eigenvalues out of. And so this is how we save computational space. We use this theorem, which states the following identity. A transpose times A times an eigenvector of this matrix equals a certain eigenvalue times that eigenvector. And if this is the case, this implies that the matrix times the eigenvector times the eigenvalue actually equals the matrix times the transpose of the matrix times the matrix times the eigenvalue there. And this identity essentially shows that if we have an eigenvector of this matrix, then this guarantees that this matrix times the eigenvector is an eigenvalue of A times A transpose. So what have we done here? Well, we have shown that for our extremely large covariance matrix, it's composed by the matrix multiplication of the list of difference vectors times its transpose. And so instead of computing the eigenvectors of these directly, we can simply say compute the eigenvectors of the much smaller A times A transpose, which in this case is only 76 by 76. And so the eigenvectors of this matrix will actually be A times the eigenvectors of the original matrix, this one, our covariance matrix, because V equals, this is the same V in both cases. So after we do this, we simply multiply AV by the inverse of A, or another way to get back our original eigenvectors. And we can use these eigenvectors to now perform our recognition procedure. The eigenvectors we have just computed are the eigenfaces. And in a high-dimensional cloud of difference vectors, these represent the orthogonal directions where the dataset has maximum variance. So those are our some of our eigenvectors, let's say, eigenfaces, specifically. So the first eigenface, that is the one with the, I believe it's the largest eigenvalue, is the direction where faces vary the most. The second is the next most orthogonal and most varied direction, and so on. And so yeah, so the eigenvalue equation can be summarized as the covariance matrix times the eigenvector or eigenface equals that corresponding eigenvalue times that corresponding eigenface. And this is quite interesting because now instead of having our data as a 36,000 pixel descriptions, we can simply decompose any face vector into a linear combination of our 76 eigenface vectors. So we can describe any face as using our 76 faces in the dataset. So that's very interesting. Finally, let's see what happens when we input a face vector into the algorithm and how we use these eigenfaces to recognize what face that is most likely to be. So we start with an image, then we get a face vector v. So to recognize this new face, we simply subtract the mean face to get the difference face. And then we write the difference face as a linear combination of all the eigenfaces because the difference face is guaranteed to be in the subspace spanned by the set of eigenfaces. So yeah, we project it onto these eigenfaces. E, I guess. E is fine. And then we can have these sorted in order of importance so that we don't have to compare with all the eigenfaces if we don't want to. So now, simply by comparing each coefficient to known faces expressed as the same kind of linear combinations with their difference faces, we can then see which face the inputted face is the most similar to by simply looking at some thresholds or other ideas. So that is pretty much how to use this method to recognize a face. So I'm gonna finish by discussing some applications of eigenfaces and how they have led to advances in modern deep learning. Here we've discussed facial recognition, but obviously it can go far beyond faces. It can be used to classify gender from faces, or it could be used to simply recognize other images if a proper dataset is fed into it. Finally, eigenfaces can even be used as a method for image compression. Um, we have reduced an image from 36,000 data points to 76 coefficients that are basically the coordinate vector corresponding to the basis of eigenfaces. And yeah, we've basically done a change of basis matrix here actually. So we can store these images in using quite a little bit less space. Eigenfaces are actually quite a primitive facial recognition technique. Nowadays, and convolutional neural networks are often seen as the industry standard. And this is because eigenfaces often miss certain aspects of the images that machine learning can pick up. But the fundamental ideas of reducing this dimensionality, using the eigenvectors and covariance, these are still very important in today's techniques. So, yeah, thank you for listening.